Hey everyone! In this video, I want to answer 3 very concrete questions about cross-entropy loss. First, what exactly is empirical cross-entropy? Second, why do we use empirical cross-entropy as a loss for classification? And third, how is it actually derived? Not memorized, but derived from first principles. Let's start with binary classification. We model the label y as a Bernoulli random variable with parameter p. Here, the model predicts a probability of p when y equals to 1. And the model predicts a probability of 1 minus p when y equals to 0. If the model follows the Bernoulli distribution, then the likelihood of observing y is given by this expression. In statistics, learning means maximizing likelihood. Equivalently, we minimize the negative log likelihood. When we take the negative log of the Bernoulli likelihood, we get this expression. This is the binary cross-entropy loss for one sample. So binary cross-entropy is not a heuristic. It is the negative log likelihood of a Bernoulli model. A common question is, why not just use mean square error for classification? Look at what happens when the model is confident and wrong. Let's consider y equals to 1. When p is closer to 0, we can see that the BCE explodes. The loss becomes very large. However, the MSE barely changes. Classification should strongly punish confident but wrong predictions. That's why we prefer BCE loss over MSE loss for classification. Now let's zoom out from binary classification. In general classification, the model outputs a probability distribution over classes. The target is not a number. It's a one-hot distribution, but it's still a distribution. So classification is fundamentally a distribution matching problem. Once classification becomes distribution matching, we need a way to measure how different two distributions are. One natural choice from information theory is KL divergence. Let's consider we have two distributions P. We have predicted distribution Q. KL divergence measures how much the model's predicted distribution Q disagrees with the true distribution P. This is the formula of KL divergence. Let's understand this formula using a concrete example. This is a true distribution P. This is our predicted distribution Q. Now let's assume P is fixed and Q moves from the wrongish distribution Q0 to the perfect match distribution Q1. This is how the KL divergence changes when the Q moves from Q0 to Q1. As we can see, as Q gets closer to P, the KL divergence decreases. When they match exactly, the KL divergence is 0. So, KL divergence is minimized when the model distribution matches the true distribution. From KL divergence, we can obtain cross-entropy. This is the definition of KL divergence. We can expand it into this form. The first term is the negative entropy of P. It's a constant. The model cannot change it. The second term is the cross-entropy between P and Q. So this is the cross-entropy between P and Q, and this is the KL divergence from P to Q. This is a constant. So we can see that minimizing KL divergence is equivalent to minimizing the cross-entropy. Here is one practical problem. How do we compute cross-entropy empirically? We don't know about the true distribution P. We only have samples y1 to yn from it. These samples follow the true distribution P. By law of large numbers, we can see that this empirical expression converges to the expectation over P. So, we can approximate the cross-entropy between P and Q by this empirical expression. This is called the empirical cross-entropy. And this is exactly what we compute during training. Binary cross-entropy now falls out naturally. For binary classification, each label follows a Bernoulli distribution. We can calculate BCE loss via substituting this Bernoulli distribution formula into the empirical cross-entropy formula. So this is our expression for the BCE loss. Notice that in the BCE loss, we average over n samples. A large n is required for the law of large numbers to hold. At this point, you might ask, why not just minimize KL divergence directly? KL divergence requires knowing the true distribution P. But in practice, we only see samples. Cross-entropy can be estimated from samples. However, KL divergence is hard. This is because KL's log error also depends on P. Let's summarize. Classification is a distribution matching problem. KL divergence measures the distribution mismatch. And cross-entropy is the practical loss that let us minimize KL divergence from data. For classification tasks, cross-entropy is a better loss than MSE. This is because cross-entropy punishes confident wrong predictions more than MSE.